and a simulated Valentine's Day party run by Stanford researchers, an AI agent confidently prepared to discuss a specific topic at an upcoming event. Yet when queried about the event itself, the system threw a null return. The agent planned to attend a party it had completely forgotten existed. This contradiction indicates a precise memory indexing failure. The agent successfully retrieved an isolated fragment of its intention, while failing to pull the parent memory that provided the necessary context. True system statefulness introduces structural failure modes that are distinct from traditional generative model errors. When an architecture includes a memory layer, the primary challenge shifts from predicting tokens to managing data retrieval and consistency. I'm the bearded AI guy. Today, using research compiled by the human architect, we are deconstructing state maintenance in metacognitive agents. The primary engineering bottleneck in deployed AI right now is the transition from isolated single-pass workflows to continuous stateful agents that operate over days or weeks. Treating this as a simple storage problem is a mistake. Simply bolting a vector database to a large language model and dumping every chat log into it rarely creates a functional cognitive brain. Flooding the system with a high-entropy flight recorder fails. Real agent continuity requires a highly organized meta-layer digest. Passive archiving actively degrades an agent's ability to maintain continuity. A coherent system demands aggressive context orchestration to surface constraints and pass decisions precisely when needed. Every large language model operates under a strict mathematical constraint, a finite context window. Over an extended task, this working memory inevitably reaches maximum capacity. MemGPT treats the context window like RAM. Nearing capacity triggers a memory pressure alert. The agent extracts key facts into a permanent partition, a persona block, flushing the active queue. Later, a search command pulls targeted historical data back into the active prompt. Deployed agent memory operates as a mechanism for paging data to a hard drive to prevent a total system crash. Storing facts is only half the architecture. To build a system that improves from its mistakes rather than just recording them, we have to look at procedural memory. In Generative Agent's Reflexion tree, raw observation logs at the bottom are mathematically evaluated for importance, converging into a synthesized apex node. These self-notions move into an episodic buffer, acting as strict behavioral guardrails for the next attempt. This engineering loop allows an agent to compound its abilities over time. It refines its execution across multiple trials, entirely without altering the underlying model's neural weights. By compressing raw experience into durable lessons, the meta layer stabilizes the agent's identity. The system bypasses the need to relearn its own operational rules on every single inference pass. A stateful system carries inherent risks. If an agent treats its stored meta layer as an absolute ground truth, it becomes susceptible to malicious manipulation. Researchers at Palo Alto Networks Unit 42 documented this vulnerability through the Environment-Injected Memory Poisoning Framework, or E-TAMP. An indirect prompt injection embedded in an external web page is ingested during a normal observation phase and silently archived into long-term memory. When queried later, this dormant corrupted node is extracted, silently overwriting the agent's core system instructions. Moving from a stateless to a stateful architecture transforms memory into a persistent, cross-session attack surface that requires layered security mitigations. Zooming out to evaluate the human architect's core thesis, we can see the strict reality of system statefulness in production. The underlying large language model remains a completely stateless mathematical function. It is unaffected by the passage of time or the accumulation of previous tasks. Memory is a ruthless orchestration layer, a system designed purely to filter, synthesize, and route tokens into a highly constrained window just in time for inference. Metacognitive agents demonstrate high capability when their meta layer holds true, yet remain fragile because every future action is entirely downstream of their retrieval algorithms. Subscribe to the Bearded AI Guide channel for more deep dives into the architectures driving autonomous systems. Drop a comment below. Let me know which engineering bottleneck I missed, or tell me which complex agent framework you want torn down next. A final thank you to the human architect for providing the research and source material for this episode. Until next time, keep your logs clean and tightly monitor exactly what your agents are writing into persistent storage.